In this lesson, I cover some background on reliability, availability, and maintainability. So this is mainly a theory of operation lesson. Then in the following lessons, we put this to practice. So let me quickly go through an outline of this lesson. I start with some what I call facts of software life. Depending on where you are in your career, these might be interesting takes, or it might just be obvious stuff. Now there's a lot of terminology in this course, starting with the title, and we go over those terms. Then I give an introduction to fault handling, as that is an important topic in this course. Then I discuss maintainability support for non-fault scenarios. And finally, there are some prompts or questions for you to consider, and for each one I give you my take on it. Here I want to discuss some facts of software life. When I entered embedded development, I really knew nothing of this stuff. So the first thing is, in systems with complexity, there will almost always be bugs. New features can often produce new bugs. That's sort of not surprising. But bug fixes will sometimes lead to new bugs. That's a little bit more surprising, but it's the whack-a-mole problem. You fix a bug and it has some side effect that creates another problem. Now this is why sometimes in development processes, when you get close to a major release, you don't fix minor bugs, because you don't want to ship a major release and then find out that a minor bug you fixed at the last minute actually had some subtle side effect that was actually worse. Products will often ship with some known non-serious bugs, and the bugs to worry about are those that are unknown. If you know about the bug, it's usually not a big problem. Another principle is that weaknesses in defensive programming are bugs. And sometimes it takes a little bit to accept that. Now, external devices or systems will sometimes not behave as expected. That's reality. And there's an interesting statement in an RFC from the IETF that says, in general, and this is for networking products, in general, it is best to assume that the network is filled with malevolent entities that will send in packets designed to have the worst possible effect. Now, with security attacks, that's of course completely true. But even systems that are trying to play nice may send you packets that they think are okay, but that cause you havoc. So if your code can't handle in some reasonable way unexpected or even wrong, I put wrong in quotes, behavior in an external device or system, you have a bug. Now the same thing goes for users. They will not behave as expected. And sometimes there'll be a problem reported, and you think the user did something that just makes no sense at all. But it's your job to deal with people doing things that seem to make no sense. So that's defensive programming. And then a final thing is that analysis of potential failures is critical for many embedded systems. And it should always be part of your development, even if the system is not considered safety critical. And you have to think about what kinds of things can go wrong. And your answers to this question, some of it's based on your experience, some of it is just based on looking at the system and thinking it through. And then the follow-up question is, how can I detect and react to these kind of failures? Now I have several slides on terminology. This might not be the most exciting stuff, but if you're a professional engineer, it is important to understand terminology so you can communicate precisely with others and read articles and so forth. So I'm going to start with reliability. This is the ability of the system to function without failure. Now in our case, a failure might be a system crashing or just doing something wrong. It's measured in principle in failures per unit of time. So there is this term, mean time between failures, MTBF, which is a measurement in years, for example. So in other words, you expect a failure every 5 years. This works for hardware and other kinds of things that wear out It's hard to apply MTBF to software. It just is a different thing. Um, Now, reducing failure rates, for example, by increasing code quality, is critical to increasing your reliability. But a reliability plan based on bug-free code is usually just unrealistic. Now, there are general techniques to reduce failures besides just writing better code, and I've done some of this. A good example here is protection against double freeze in systems with heap. So in this case, there might be a bug in the code that does a double free, but you have some preventive code in there that will prevent it from actually doing any harm. So in this course, we just assume there are going to be failures and we focus on how to deal with them. So the next step is, or the next term is availability. And this is the ability of a system to function at any point in time. It's measured as the percentage of the time that the system is functioning or the percentage of time that it's up. Now, this is affected by MTBF. If you don't have any failures, you're 100% available. And it's also affected by the mean time to repair. In other words, once there is a failure, how long does it take until the system starts running again? And of course, that can depend on many, many things depending on the technology. In this course, we focus on the detection of failures and automatic repair to reduce mean time to repair. And this is things like an automatic system reset. So continuing on, the next term is maintainability, which is the ease with which a problem can be corrected. There are different points of view on this, and I'll address two of them separately because I want to make it very clear. From the customer's point of view, maintainability relates to the features and tools that are provided to easily diagnose and fix problems, such as configuration and installation errors, hardware problems, or problems with an attached system. We generally don't expect customers to find software bugs. They might, but the things listed above are generally the problems they deal with. Now, there should be explicit product requirements for these features and tools as they are really a part of the product from the customer's view, just like the product's normal operation. We aren't so interested in this course in the customer's point of view. We're more interested from the software developer's point of view. And in that case, maintainability relates to what features and tools are provided to diagnose and fix software bugs. And there are scenarios like this. A system has some problem while running, and you fortunately have some kind of access to it, say it's in a lab, and you want to get information from it while it runs. You need a way to get that information. Another one is the system has experienced a failure. It has restarted itself and it's now again running fine. This is generally the more difficult scenario, and you really desperately need some information. So usually it is up to the development team to address these features and tools. There's usually no written requirements because normally no one outside the development team really is that concerned with how easy it is to maintain the software. So one of the things I mentioned here is that sometimes when we talk about software maintainability, you tend to think about things like code quality and the development environment, how easy it is to read the code and to test the code and so forth. Those are very important things, but those are outside the scope of this course. This is the last slide on terminology, and here I cover a few more terms beyond reliability, availability, and maintainability. The first is safety, and this can be defined as the ability of a system to not harm people, the environment, or other assets. Now, that's not the focus of this course because with many systems, safety is not a big issue. Also, it quickly becomes application dependent. Also, I've worked on systems where safety was an issue, but it wasn't a primary issue, and so I feel I just don't have sufficient experience in this. Two other terms you'll hear are resiliency and robustness. Now, generally, these relate to the ability of a system to function in the face of adversity. Now, this leads to the question of what is the adversity? And that's what makes these terms a little bit vague to me. The adversity could be the unexpected behavior of an external device or system, or the adversity could be some software getting stuck in a loop. Perhaps you could say that resiliency and robustness are two things needed to achieve reliability and availability. And then the final term I want to discuss is non-functional requirements. And I bring this up because I actually worked many years for different companies and never heard this term. We didn't use it. And when I first heard it, it sounded a little bit odd to me. But a non-functional requirement is what the system, not what the system must do, but how it must do it. So it tends to include things like reliability, availability, and maintainability, as, as well as many other topics such as security and safety. Now, these non-functional requirements, like all requirements, tend to be from the customer's point of view. But there can also be non-functional requirements for a software design from the developer's point of view. And this would be things like those features and tools we discussed that are needed to help diagnose and fix bugs. Now I want to provide some background on fault handling, as it is a key topic in this course. This is just an outline of the actions that are part of fault handling, and I discuss how they address some of the system properties we have seen. So first, obviously, you must detect a fault, maybe using techniques covered in this course. This addresses availability because to ensure high availability, you have to know when something is wrong. When I worked in communications, the worst field events we had were when the system was messed up in some way and it wasn't working right, but it didn't know it. So the techniques include things like watchdogs, CPU exceptions, and maybe various things the application is checking on. Next, once you've discovered a fault, you need to collect information. This addresses maintainability because this information will help developers diagnose and fix the problem. And this information can include return addresses, CPU registers, fault registers, circular buffer logs, and so forth. And then finally, you perform recovery actions based on some policy. The policy will depend on the nature of the system and also what is practical. So one policy is a fail-safe policy, which addresses safety. So in this case, if a fault occurs, the system will shut down in a safe manner, such as all outputs off, and will stay idle. The hardware design might play a big part of this fail-safe policy, by the way. So some hardware or software reset might be done, but the key is the system will not restart operation. Some higher level action, such as a person, is typically required to restart operation. For example, I worked in robotics for some time. The robots worked in factories, and if a robot controller experienced a fault and stopped in the middle of a task, it would just stay there, and people would have to get involved to sort of get things back and going again. And sometimes it was not simple to get that going again. So fail-safe is commonly used in systems where safety is of most importance. Makes sense. So another policy is automatic recovery and restart, and this addresses availability. In this case, if a fault occurs, then typically a hardware or software reset is done for part or all of the system, and it attempts to automatically restart operation. So this is commonly used where availability is of most importance. And that includes things like communication systems, entertainment systems, some consumer electronics. I worked many years in communications, and this is the norm. Here I'd like to discuss some fault handling design principles. Fault handling code should be of the highest quality, however you achieve that. Bugs in fault handling code can be especially costly because it can leave a sick system in some zombie state, and that's the last thing you want. You should keep your fault handling code simple and simple for others to read and understand. It's not a good place to be clever. There are many advantages to a single recovery action, that being a full hardware reset. I like to do that if it's acceptable, and that's what we do in this course. If you do something less than that, like let's say you are having problems talking to a sensor, so you reinitialize an I2C controller, then normally, if that doesn't work, you later have to escalate to a full reset. And that is a much more complex design. Of course, sometimes you really need to avoid a full reset if at all possible. So it's worth it to start small and escalate only if you need to. So now panic mode operation. Often when a fault is detected, the overall integrity of the system is in question. For example, any data in memory might be corrupted, so hardware drivers might not work. In panic mode, we try to get the system into a basic sane state and then operate simply, trying to depend on as few resources as possible. So for example, we immediately disable interrupts. For all future operations, we do them in polling mode. For example, we have special panic versions of console and flash output functions that poll, and of course they block, which we normally don't do. If there's an RTOS, disabling interrupts should stop scheduling, but you need to make sure that's true. We need to make sure the stack pointer is valid. Maybe there's something has went wrong with the stack, and normally we just set the stack pointer to its initial value like we would on power up and just more or less start over with the stack. Possibly we should reinitialize any peripherals that will be used, for example the UART. Now, I didn't do that in this course because of the way the hardware initialization code is organized right now, but it's a good idea. And then finally, if available, have a hardware watchdog timer running as a backup. So if something goes wrong and your fault handling gets stuck or whatever, the watchdog will hopefully reset the system. So far, we've been discussing mainly fault scenarios. So I want to discuss maintainability support for non-fault scenarios for just a bit. These are techniques I used in my work and that I'm now using in my YouTube courses. First, it's key to have a console and console commands. That's your window into the system. And with today's MCUs, consoles have very low cost. Now, the console commands are typically used to get the internal status of the modules or to control logging. Speaking of logging, multi-level logging on a per module basis is important. It allows you to walk up to a system and turn on logging on some module at some level and find out what's going on. Often the console is the logging output device, particularly for small systems. And if you can arrange to have logging to a USB drive, that's really convenient for lab and field systems because someone can put the USB drive in and take it out and bring it back to your lab and check it out. And of course, USB drives can hold a lot of data. So the last thing I wanted to mention is performance measurements, or PMs. And PMs are commonly counters of unusual events like bus or communication errors. They can also be flags that are true when some unusual condition is present, like an alarm. PMs are often displayed and reset using console commands. So PMs are convenient to check on a system that's been running for a long time and just see if it experienced anything, any issues. They can also be used when debugging a communication interface. For example, a serial interface, you can look at the PMs for that serial interface and seeing if it's getting framing errors or whatever. Here are the prompts or questions for this lesson. I will just pause here for a moment and then go through them one by one, giving my take. The reliability of a product is sometimes the best when it enters a maintenance support only phase. Why might this be? Well, when in maintenance support only phase, software updates are only, in many cases, only for bug fixes. So with no new features, fewer bugs are being introduced. So overall, you're reducing bugs. And I've seen this in products where new feature development has stopped, but maintenance releases still go out. And yes, they get very reliable because the number of bugs that are causing problems just continue to decrease. If a system is to be 99.999% available, and people refer to this as 5 nines, how much time per year can it be down? Well, the calculation is pretty simple. 365 days, 24 hours, 60 minutes, and this is the percent of downtime, and that's 5.25 minutes per year. So 5 nines availability is often expected for communication network equipment, and it is often achieved using redundant hardware that can be switched in or replaced while the system is running. Say a system is running but can only perform 50% of its normal capacity. How should this be treated from an availability viewpoint? Well, this only applies to systems where there is a concept of being partially working. Some systems, they're either working or they're not. But let's say a communication system might be one where it can be 50% of its capacity. So sometimes the availability is prorated, such that if the system runs n minutes at 50% capacity, it only counts as n over 2 minutes of downtime. These things are important when you have agreements on what the downtime is of a system. Now, for large distributed systems, it might be possible to take down parts of the system in stages and do hardware or software updates piece by piece. This, depending on exactly how availability is measured, this could reduce or actually eliminate downtime due to a software update. With a communication device, if all communication links are down, should you consider treating it as a fault? Well, normally, no. You would assume the problem is external. Why would you view that as a fault? But there is a chance that the problem is actually in your system. If your system is not doing anything useful anyhow, you might consider treating the condition as a fault, say after 15 minutes, and go through a reset. I worked on a system once. I joined the project after the product was established. And I noticed the first time I was doing some work in the lab is that some of the communication processors were resetting. And it was something like every 15 minutes. And of course, I thought, what's going on? What's wrong? So it turns out they were using this strategy. Well, this is the end of the lesson on background on reliability, availability, and maintainability. I hope it was useful to you, and thanks for watching.